about. I don't know why. I don't remember talking about it in the last presentation. And there was the different types of jackets that you have. And we looked at it. Huh? I don't know. I don't remember changing this one. Again, this will be in the last chapter, not the one that we were working in last class before the final. Before the. I think we went over this, the basic equivalent circuit for twisted pair. This is the equivalent circuit for coaxial cable. Now, whether you understand this or not, what it does is it sets up an impedance. Y'all understand the difference between impedance and resistance? So what's an impedance? It's an opposition in an AC circuit, right? You understand that? So impedance of what we have in AC is we pick up what we call reactance, a reactive component, which basically deals with these little curly things. These are inductors, and then these guys right here, these are capacitors. And what we would have to do is at a certain frequency, this cable would have a certain impedance. Not resistance, impedance. It don't have impedance in DC, right? You understand? So if I was to take an ohm meter on my coaxial cable and I was to measure from this wire right here out to the shield, it's going to measure an overload because you're trying to measure resistance, right? You understand that? Right? Everybody understand? If I was to measure from one end of the cable over to the other end of the cable, then I would measure the resistance of the wire, which is almost going to be nothing, right? You understand? But if I was to put AC on this sucker at a certain frequency, then it would have a certain impedance. And we call that the characteristic impedance. And our ultimate goal in a communication system is to get what we call impedance matching. We looked at that, right? What happens if all the impedances match? So we went up there, we threw up all them different resistors. We had an internal signal source that had 100 ohm worth of resistance because it's easy to see resistance. And then we put about 4 or 5 different loads out there, 3 different loads, and we saw when we got the maximum transfer between our transmitter and our receiver. When did that occur? Y'all remember that guy? We did it in some class. I could have swore it was in this. Impedance matching. So this is the cable splice and insulation. And we went through there, and we went through this guy right here. We didn't do that? Okay, well, let's go ahead and go through it. Now, sure we did. We haven't been on this. We did do DB, right? DB? Yeah, we did. Okay. Well, what we're going to do is we're going to come up here, and the power transfer between a transmitter and receiver is maximum. Let's see. What we're going to do is let's just skip over this and do this. What I'm going to do, I'm simulating a signal source, and of course it's AC, but we're going to do this with a resistor. And what I'm going to do, and every signal source has a opposition, right? You understand that? We can't get away with that. We don't regulate our signal sources to make them appear like they have no opposition. Okay, so what I'm going to do out here on the output here is I'm going to put 3 resistors. I'm going to start off with a watt, a 10 ohm, then I'm going to go to 100 ohm, and then I'm going to go to 1,000 ohm. Okay. And then we're going to calculate how much power we get to the load. So my load is over here. Right? This is the internal resistance of the signal source. And we can imagine that as being the impedance. But here, since y'all know DC, we know how to calculate that, right? I'm going to put that 10 ohm out there, and what I'm going to do is how much power would I get to that 10 ohm resistor? Now, what we're going to use is instead of trying to use Ohm's law to calculate this, we're going to use a formula called the voltage divider formula, and this works for series circuits. And what's nice about that is we can do a lot of the math in our head. Everybody, did y'all get the voltage divider formula? What's the voltage divider formula? Anybody know it? This one you should keep in mind. It's just in a series circuit and when you get into solid state and we start doing transistors and stuff like that, understanding this formula is going to save you a lot of time. So what we can do is we can in a series circuit, I can take any resistor. So how much voltage does the 10 ohm we drop? Well, it's relative to the amount of resistance you have in the entire circuit, right? You understand that? And when I teach DC, that's one of the most frustrating thing I teach is I'll come up here and I say, okay, I've got this circuit and I got a 10 ohm resistor in series with a 100 ohm resistor. And they'll do all this calculation. And then I'm going to replace this 100 ohm with a 200. What's the voltage drop across the 10 ohm? Well, they'll say, well, what's the current through the 10 ohm? Well, they'll say well, it's the same because current is constant in the series circuit. So some people's got the impression is once you calculate the current in a series circuit, it's the same no matter what I do to the circuit. The code depends on the circuit. In a series circuit, it depends on the circuit, right? So here the load is out there. That 100 ohm is representing the internal resistance of the source. So this would be like the internal resistance of a battery. So have you ever got a battery and measured across the output when it's new? It's going to measure about 1.65 volts. As soon as you load that sucker down, that voltage is going to drop. Why? Because of the internal resistance of the battery. They have it. Now, we fake that out with something that's dynamic, like the alternator on your car. When you turn on your lights, we got what we call a voltage regulator that senses when the voltage tries to go down, and it puts more energy into the generator to make it maintain that, right? You understand? So if I don't have a regulated circuit and I've got a power source and I don't have a regulator, then as soon as I put a load on that, the output of that voltage is going to drop. Okay, you'll understand that. Well, a signal source is not regulated. How can I regulate these radio waves that's coming through the air? Right? You understand that. So these guys come in, right? You understand that. Or I come over my cable TV. How do they know how to regulate that? They're not at your house. They don't know what you're getting out there, right? You understand? So they send the signal out that cable. So as soon as I load that signal, what happens? Well, it's going to drop. Now what we're trying to do is we're trying to get the maximum power transfer I can get to this 10 ohm resistor over here. Because this is the load. This is where I'm trying to get this to, right? You understand? Okay, so what would it be? So if I'm going to put the 10 ohm, the 100 ohm, and the 1000 ohm, which one would give me the maximum transfer to the load? What would you think, Dwayne? 10 ohm. What do you think, Charles? I'm going to put a 10 ohm, I'm going to put a 100 ohm, I'm going to put a 1000 ohm. Well, we can do it in tenths of an ohm, too. What would you think? Oh. Which one are we going to get when I change these resistors out here, which one's going to give me the maximum transfer to the output resistor? Gordon? What do you think, Brian? No, which one? Okay, the 10 ohm. What do you think, Henry? Huh? 10 ohm. Okay, so let's calculate that. So what we're going to do is we're going to calculate the power to the 10 ohm resistor. So what I'm going to do is I'm going to use the voltage. I'm going to use two formulas, and that way you can key them in without changing anything on your calculator, without using parentheses or anything. So the voltage divider formula says the voltage drop across any resistor is equal to that resistor relative to the other resistors in the circuit, and that would give me the ratio that resistor would drop. Is that at 10 ohms or, well, that's at any voltage, and that's what's cool about the voltage divider formula. And this is the problem we have at in DC, is I say, okay, I've got a 10 ohm resistor, I've got this series circuit, and okay, what's the voltage drop across the 10 ohm resistor? And you calculate all this. And I say, what would happen to the voltage drop if I change my input voltage to 20 volts instead of 10 volts? Well, most people would go through and do all that calculation. But if you did this right off the bat, I could put any voltage on that circuit, and that resistor would always drop that percentage of that voltage, no matter what the input voltage is. And we call this the voltage divider formula. So what I would do here, what are we trying to find out? We're trying to find it across the 10 ohm. And this is what the beauty of this is, most of the time you can calculate RT in your head. So I'm going to take 10 ohms, and I'm going to divide that by, 110 ohms. And then Then that would give you the ratio of the voltage drop. And then you can take that and you can multiply it by the applied voltage, and that gives you how much that would drop. Which is going to be 1/10 of, so I know already it's going to drop 1/10 of the voltage. Without, just by the ratios, right? You understand that? So how much voltage would it drop? What's that? 900, not 0.900 milli, right? What's that? 90 milli. Anybody else got? Huh? Yeah, we'll do science. We do scientific notation. Okay, 0.909.
Yeah. 909 milli.
909 milli, right? Okay. Okay, so what I'm going to do now, don't do anything with your calculator, is I'm going to use a formula right here where I can one of my power formulas is V squared over R. So what I can do now is I can just hit my square key and I can divide that by 10 and that'll give me the power. So I can do this without using parentheses, right? Okay, so what would be the power to the 10 ohm resistor? Okay, 82.6 milliwatts. Okay, so here's the math. I came up with 83 milliwatts. Are we okay? Okay, okay. So what we're going to do is we're going to take that thing out and we're going to put the 100 ohm resistor in there. As we get that 100 ohm resistor. Now let's calculate the power to the 100 ohm resistor using the same formula. So here I'm going to say what? I'm going to say what? I'm going to say 100 over 200, and we can do this in our head, right? Times 10. So that's 5 volts. I'm going to take 5 squared, and I'm going to divide that by what? 100, and what's the power? What's that?
250 milli.
250 milli. So right off the bat, you know the 10 ohm is wrong. So at the 100 ohm, I got 250 milliwatts. At the 10 ohm, I got 82 milliwatts. Okay. So let's do the 1000 ohm. I need to turn off my touch screen. It keeps messing me up. Okay, so 250 milli. Okay, so now we're going to put the 1000 ohm in there. So here I would say, okay, my voltage drop is going to be equal to what? 100 over 1100. And then I'm going to multiply that times 10. And then I'm going to square that answer. And I'm going to divide that by 10. So did you say we can do that whole thing with just right down the straight, right? And it should come up to be about 82 milli again. Of course, y'all said 82. My math said 83, and then I put 82 up there, but that's okay. So what did y'all come up with? I think it's around 82 milliwatts again. Right? 82, 83 milliwatts. So when do we get maximum power transfer? When what's important is when the resistance of the load matches the resistance of the source. So instead of communication, we don't arbitrarily let that happen. We set the communication of the system. So if I use 300 ohm cable and I have a 300 ohm output on my amplifier and I have a 300 ohm input on my receiver, then we get what? The maximum power transfer I can possibly get in that system when the impedance matches. Well, I just threw up 3 numbers. We could go in tenths of ohms, we could go in thousandths of ohms, we could go in millionths of ohms, and you would get the maximum power transfer when the impedances in the system match. Y'all understand that? Now in power, we're dealing with R, and we're still dealing with impedance, but we're dealing with almost no resistance at all. in a because I can deal with a regulated power supply, right? You understand? So my power supply can compensate for impedance in the system. DC, we don't have to worry about impedance. DC, so people say which one is the most efficient to transmit. DC would be so much more efficient, but you can't step it up and you can't step it down, right? You understand? So AC, it's more efficient to transmit because we can do what? We can step it up to transmit it and then do what? Step it down to use it for safety. But there are some underground cables, I think, going over in Europe through the English Channel. They're using DC because they don't have to worry about impedance. They don't have to worry about impedance. What they do is they electronically do what? They electronically rectify it with the diode banks, and then they get on the other side, they invert it with kind of like an inverter you have in your car, that you can take your 12 volts and use an inverter and convert it to 120, right? But they do that because they don't have to worry about this thing called impedance. But if we can match the impedance in the channel, then we get maximum transfer. So that means these cables, these coax cables, they have a certain impedance at a certain frequency, the frequency of the carrier. And then these twisted pair cables, they have a certain impedance, right, at a what? At a certain frequency. And that's what, if everything in the system matches, then that means you get maximum power transfer. I think, the story I tell is my father-in-law was pulling a truck around the back and he broke his cable TV. He broke his TV cable. And he went out there and did what? Twisted it together. And now his picture was off. Because what did he do as soon as he did that? He broke up that capacitor inductor link that we have, and he changed the impedance of the cable. So he didn't splice it correctly, right? You understand? And so coax is hard to splice. You can't hardly splice it. You usually have to just replace it. So he finally got the people out there to replace it for him. So that's impedance matching. That's pretty neat, right? So we understand that. So now these cables. So when I deal with these communication cables, guys, you got to be real careful with how much you untwist that cable. So a lot of people, I've seen people untwist a lot of that cable to make it easier to terminate. But what did they just do? They changed the impedance of the cable. Now the system can't communicate at its rated frequency. Most Ethernet switches and everything try to communicate the best they can. So what happens if they can't communicate at a gigabit, then what do? They drop back to 100 megabits. If they can't do 100 megabits, they drop back to what? 10. If they can't do 10, then they drop down to 5, and then they say we're screwed because that's it. That's all they support. So what they usually do is they support all the channels back that was previously there, right? You understand? So impedance matching, very, 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 very important in communications. Not important in power, right? You understand? Because we're dealing with regulated power supplies and that kind of stuff. And I could have swore we went through that, guys. So when we get into these cables, it's not important to know their equivalent circuit, which is, so this is the equivalent circuit for coax. Really? Okay. This is an old slide. Undoubtedly, I remember it. Well, I'll upload this. This is a pretty interesting. So this is the equivalent circuit of a coax cable. This is not DC. This is what? AC. And this sets up a certain impedance. And what's so neat, the length doesn't make any difference. So if you had a 75 ohm cable, the way this thing is set up, and you cut it 8 feet, it would have a certain impedance. If you cut it 100 feet, it would have a certain impedance. Now what we can't do is compensate for the resistance of the cable. So the loss we get in the cable is basically because of R, not because of the impedance in the cable, it's because of R in the cable. So we still have to amplify this, right? Y'all understand? But all your amplifiers are matched to the what? To the impedance of the cable. So, my father-in-law, he was a good guy, but he tried to use his screen on one of his big screens as the antenna for his TV. So he got an extension cord and cut off 2 sides and hooked that up to his screen.
and run just a regular duplex extension cord over to the back of his TV and screwed it in there. And he had a crummy picture because he screwed up the impedance. And I think Charles was talking about he got an old 300 ohm antenna, but he's running it into a 50 ohm input. Well, what you do is you get a little transformer. It's called an impedance matching transformer that is matched for what? 300 to 50 ohms or whatever you run. The cable we used to run in networking when we first started actually running networking, we used what we call a bus topology. And basically you run one big long cable the whole length of the network, and then you just tap onto it. And it was 75 ohm cable. Well, what you'd have problems is people would go down to Walmart and buy 50 ohm cable, and they want to run a network on it. It was a 75 ohm system, and what? Wouldn't work because they screwed up the impedance matching. So these twisted pair of cables, the spacing between the twists, how tight the twists are, these guys set the impedance of the cable. So we use a lot of twisted pair of cable in communication because it's a lot cheaper than coax. So coax is hard to make because you look at it, it's made with three components, at least three components. So we have a center conductor, and then we have an insulator, which they call a dielectric, but it's an insulator. And then we have a metal braid, which people call a shield, but it's not a true shield, but that's what the trade calls it. It is actually the second conductor, and the spacing between those two conductors is what's so critical to set up that impedance, right? You understand?
And one on the bottom, that's flat cable going to the antenna. Flat cable, they have two wires.
Should be tried. This is a duplex shielded cable. The one they use, the twinplex that they use on a 300 ohm cable, doesn't have a shield on it. But the spacing is critical. You see how far those are apart, and that sets up the impedance of the cable, the spacing between that dielectric that's actually in there, that brown dielectric that's in there. This is kind of like that, but they're calling it a tri-cable, but actually because it's got three conductors, that would be right. So we're using two, but they're sharing the same shield. I didn't need it, but yes, this is the cable they use. This is one of the cables they use for DeviceNet, which is a industry standard communication protocol, where we can communicate between robots. Between robots, usually the robot controller handles that. But what we can do, so if we went over there to the big FANUC robot and you see all those directional control valves and everything, well, what they are is that we don't run a wire to all of them. We run a communication cable to them called devices. And then what we do is every one of those devices has a little address switch on it. So you address it like device 126 or device 128. And then your robot, your controller would, if you wanted to energize that thing, it would just do what? It would send out that address on the cable, and then everybody else would just do what? Ignore it. So that's one of the ways we do that. DeviceNet uses this type of coax cable too, because it's really not. It really helps us keep out a lot of electromagnetic interference. These guys are rated around 100 megahertz, which it's hard for us to understand how you can put 200 channels and all of them share it at the same time. But what we do is we ride them on a carrier, and as long as the carrier's within the range, then it'll pass it okay. So these are the different ones, RG59, RG56. RG59 is what we use in cable TV. RG58 is what we used to use in networking. We used some RG8 too, which had a lower dB loss, but it was a lot more expensive. But it was a big old cable, big old RG8. These were still some very popular coax. RG59 is very popular. And why is that? That's what cable TV uses. So we're still using RG59. RG58 used to be really popular when we first started doing networking. Topology and networking, this is the way we connect network together. And we have three basic topologies. Anybody know what they are? A topology is the way we connect nodes. A node is a device that wants to connect to the network. Is the way we actually electrically connect those suckers together. So we have one topology that we call a bus, which basically we run a common media the entire length of the network. And then what we have to do is we have to put terminating resistors on each side to keep the what? Keep the impedance on the cable. Yeah. And these are resistors because impedance is resistant, is impedance. They don't know if it's 50 ohms or an X of L or 50 ohms, right? So the terminators are just nothing but resistors. And we could go over there and look at the device net on the ABB and open it up and you'd see a resistor out there on the end. And what's that for? Well, that's a terminating resistor to make sure the impedance matches, right? And then what we would do is we would just tap off the cable. We put these taps on there. They were called T's. And then we would come down and then our computers would be down here. And this was referred to as a bus topology. Now they still use the bus topology, but they do it a little different. Now what most of the time you'll see, they'll do it as what they call a daisy chain. So what they'll do is they'll come out in there'll be a connector, and then the connector will have another connector on the back of it, and then what we'll do is this will plug into the unit, and then this will daisy chain it down. So this is still a bus topology, but they call it a daisy chain bus. And we could go over there and look at the Amatrol line, and you could actually see, well, that's not true. We got it tore apart, but it uses a daisy chain bus. It's called Profibus is what is the term they use for that. Now, star topology, which is currently the predominant topology for local area networks, is we have a central unit, and then we tap off like this. Have the guy up there, all the wires coming in? And then you would come up here, and your nodes would be out here. Or we could have another device, and we could branch off again, like that. Originally, what we call this was a hub, and the problem with a hub is that it broadcasts, when one computer broadcasts, it broadcasts through the whole network. So you'd tie up the whole network. Normally what we use now is we use what we call a router, or we use what we call a switch. And what a switch does is it learns the address of all the devices, and if this guy wants to communicate with this guy, then it'll make a patch. It'll switch it to that guy right there, and it don't broadcast over the network. So normally what we use now is we use things called switches, but it's still a star topology. And then a router lets you divide it into routes. So you divide it into what we call subnets. So what you do is when you address it, part of the address is what route that thing's on, which is pretty neat. We call those routers, which most people get in their house, but a lot of people don't understand that router. You could hook a switch to your router and hook up like 256 computers to that one port on that router. Most people hook one thing to the back of that router, right? You understand? So you got that router, it's got 4 ports on it. Now it would be a little more complicated because you'd have to set up the route IDs, and we're not going to get into that. The third predominant is what we call a ring topology. We don't run into this much, but a ring topology is we draw it like this. Of course, it's physically not connected like that, and then you have all these devices out here. And what we prevent, and the biggest one on a ring topology is something they call token ring, if y'all have heard of that. And this is basically like device networks where they pass a token, and the node with the token is the only one that can put information on the network. But what they do, and people don't understand it, is when when you send 1 million bytes of data, you don't send 1 million bytes of data at once. It's broken into what we call packets. So you send a packet. So what would happen is this guy would send a packet and then it would release the token. And then if nobody else needed to send data, they'd just keep it doing what? Pass the token, pass the token, pass the token. And when it came back to the first one, he says, okay, it's my turn again. And they would put a packet on the network. So that's the way we avoid collisions, except for Ethernet. Ethernet lives with collisions. So Ethernet works kind of like the old party lines. If you ever watched Beverly Hillbillies, when I was a kid, we had a party line. That's before everybody had, and we had a certain ring. Ours was too long and short, if I remember right. And which was really neat because you could pick it up and hold the dial and put your hand over, you could listen to people talk. But what you would do, if you played the game right, if you needed to make a call, what would you do? You'd pick up the phone, you listen. If there was nobody on it, then what would you do? You'd dial your number. If there's somebody on it, what would you do? You'd put it down. Then you'd wait a little while, then you'd do what? You'd pick it up, right? Or you might start hollering at them. Get off there. I need to make it. Okay, but that's the way it used to be until we had party lines. Well, that's Ethernet. So Ethernet, what these network cards do. Yeah. We still have one, but we do it. We do voice over IP and wires, which is what we do here. We don't do hardwired phones much anymore. But Ethernet uses a technique called carrier sense multiple access with collision detection. So it works exactly the same way. If my computer wants to put something on the network, it listens first. If nobody's on there, it puts a packet on there. Then it releases the network. Then it listens again. If nobody's on there, it puts another packet. Then it does what? Then it releases the network. If it comes up there, if it comes back here and listens and somebody's on there, then your network card generates a random number, so it don't come out at the same time. So it'll come back, wait a little while, then it'll check again. And it'll keep checking until it's free, and then it'll put another thing on the network. And which works out. So how many computers in this room right now are on the network? None. Because you're not transferring information. So if you're not sending anything over the network, your computer's basically not wanting access to the network. It's not even listening. But as soon as you say, I want to send this packet or I want to download this file, then your card connects to the network. A lot of people don't understand that either. So they think these computers are all on the network at the same time. So right now, we're not using any bandwidth in that switch right there. So that's the switch up there. See that thing? It's got all them wires running into it. Now, we originally wanted this thing wired, and that's what all these panel boxes over here on the wall, these gray panel boxes. But while I was out with my accident, they decided they wanted to go to Wi-Fi, and I hate it with a passion. And it works basically the same. So this network card wants to put something, and it's Ethernet. It's just a different version. So it wants to put something on the network. So what does it do? It listens. If you don't hear anybody else, it does what? Puts a packet. That's what. So even Wi-Fi works exactly the same way as Ethernet. It uses carrier sense multiple access with collision detection. So how many of these computers can be on the network at any one time? One. Except for the switch. Now, if I'm trying to get to that computer there, and Dwayne's trying to get to Charles' computer, the switch will switch you without us colliding with each other. But if we're both trying to get to this computer over here, then the switch is going to block one of us. It's going to say it's busy. So that's the advantage of a switch. A switch increases the speed of the network by a magnitude. We don't have that on Wi-Fi. Wi-Fi don't have a switch. Wi-Fi's got an access point. So these guys, right now, how many of you can be on this network at any one time? One. So if we all try to get on there at exactly the same time? Then you'd have problems. Yeah, well, it does it in packets. So what you would do is you'd send a little bit of your document, right? You understand? And the other person would come up and say the printer was busy. So these printers, Well, that depends on the printer. This printer that we have has network capabilities on it. And I don't know how big the buffer is on how it can buffer different jobs. So, we haven't never done that because I'm usually the only one using it. I mean, it's a good point. Token Ring does away with that because only one computer's gonna, we have no collisions on Token Ring. Because only the person that's got the token can do what? Can send stuff. Or,
So that would be slower.
well, not necessarily. You're fighting. This is what we call baseband. Now, most of y'all hear broadband, but Ethernet is baseband, which one device at a time. Broadband, you share the bandwidth of the media, but everybody, a lot of people get a little chunk. So baseband will flat wipe out broadband if you're the only person on the network, because you get the entire bandwidth. So if you got 100 megahertz, you get 100 megahertz. If you're on baseband, then you might get 1 megahertz, right, of a 10 megahertz bandwidth. But 10 people could be on there at the same time. So it's all depending on which way you go. So which one's fastest? Yeah, but that's download. Look at upload speed. They don't tell you the upload speed. Yeah, luckily it's about 25. It's about 23, 25. It's still pretty good. My router that I have actually it's got a little thing you can run that tells the download speed and the upload speed, which is pretty good. Speed test. I think it's a Lynx test. Well, what we're doing is we're dealing with this guy right here. How do we connect these networks together? Or how do we connect and this is where the impedance matching comes into play. So I just can't hook up any cable I want to, right? You understand? I got to hook up the right impedance. It's just like I was talking about. I couldn't go out and buy an RG58 cable, even though it looks the same, and hook it up to my to my TV. Because all match, the repeaters. So what these guys do, you don't have to terminate these because these are terminated inside the computer.
My question is, between one of the connections, the wrong cable.
Then you kill, and a ring, you really got problems.
Oh, you get one different cable, just
yeah, one thing messed up. So most of them run what they call it's a dual channel Token Ring. So you have a backup channel. So you have one channel going, and the other one rotates in the other direction. It's really neat. And if you have an open, I'm sorry, it'll automatically, this guy will automatically switch you over to the other one and send you back in the opposite direction. If it can't get all clear. So y'all learned a little bit about networking. So what would be nice about the bus topology is we can connect things and disconnect. Let's go over there now.
I don't know if you could look and see exactly what we got on our platform.
I can.
A lot of our slides come up short compared to what you got.
So these are this is twisted pair cable. And maintaining these twists is what's important, right? You understand that? Because if you untwist that cable too far, just what you did, you change the impedance of the cable and the system can't run as fast. We're going to build. This is called UTP, this is unshielded twisted pair. This is, and then we have categories of twisted pair.
Now, on that twisted pair, if you untwist it, what if you cut back an inch? Still twisted.
Yeah, it's the same. It's not set by the jacket. It's set by the spacing in this cable right here. So it's not how far you cut back this jacket. This jacket has nothing to do with the impedance of the cable.
I'm sorry, if you had unwound, or you were working on somebody else that unwound it, you don't know how many winds to get it back right. What if you cut back to the good wire?
And then count them, you could do that per inch. That's what you're shooting for, is so many twists per inch is what you're shooting. So you could get it close. It would probably be better than leaving it untwisted, in my opinion. Are we okay? This is pretty standard on cable we use for networking. This is called shielded twisted pair. Now, STP cable has the ability to work in extremely noisy environments, right? Y'all understand that? So, like if I'm going to run EMI, well, that would be that, EMI. The problem we have in industries, we have all these motors and all these things that unshielded, and we're putting all this stuff on there, and they generate all this noise, right? Brittany's got my oscilloscope over there on the side, I guess. But if I had an oscilloscope that has a real high impedance on it, and I touch my finger on it, it's going to pick me up. It's going to be 60 cycle, because 60 cycle is being broadcast all through this building. Right? You understand? Thank goodness. We have a capacitive effect, so I'm picking up these signals. Which means what? I can use those to do what? Make this touchscreen. So this is a capacitive screen. We have resistive and we have capacitive. Resistive is a lot better. It's a lot noisier because you got to push on it. So if we went over to that HMI panel, it's industrial panel. They don't use capacitive. They use resistive. So you have to literally do what? You have to press that. What can you do with this guy? You just slide your hand across it, because what you're doing is you're setting up a capacitor. So I'm receiving 60 cycles right now, and if I can set up a way to sense that here, then I can do what? I can use the touch screen. So the shielded twisted pair, if we're going to be in an industrial environment and we're going to run Ethernet, which uses twisted pair, then what we should use is shielded twisted pair. And all our switches and all our network components should be set up to handle shielded twisted pair. So they have what they call this cable right here. This comes with our PLC. This is shielded twisted pair right here. And when we pass it around, you look, it's got this metal on it. And what this is the shield. And if we went over there and looked at an industrial Ethernet switch, it's going to have a metal jacket on it. So what we do is we connect the shield through our switches and our devices, right? This is a standard network cable right here. So this is UTP, which is what? Unshielded twisted pair. This is STP. It's not the racer's edge. This is shielded twisted pair. In commercial Ethernet, you won't run into this. In industrial Ethernet, this will be the cable. Quite a bit more expensive. We're not going to cut this one. We got some UTP. We're going to deal with UTP. We're not going to deal with it. So these are the speeds. So UTP voice, this is what you use. So we use twisted pair on our phone. If you got a hardwired phone, you use twisted pair. Right? You understand that? Anybody still got a hardwired phone? I do. Well, that uses twisted pair. And we'll see people get those things out of the twist, and they'll untwist it a long way, right? In fact, who did it? Me. We'll realize, so UTP, this is voice. This is good for 800 meters. Cat 3, which is what we use for our first networks, category 3 network cable. This was 5 to 16 megahertz, which got us up to still 90 meters. 90 meters, I'm not sure. I always heard 100 meters. That's what I learned was, huh? Well, no, what happens at 90 meters is it's not the impedance, it's the R of the wire. You've only got a certain allowable dB drop over that length, and if you get past that dB, then there's no guarantee that the receiver is going to receive the data. It has nothing. The impedance of the cable don't change because of that network, which is so dang cool. So I can have a RG59 It's 50 ohm whether I have 8 feet or whether I have 100 feet at 100 megahertz. But the R is what gets us, right? Because if I try to send a signal through a cable, there's got to be current involved. We try to make the current as small as we possibly can make it on network, but there's still got to be an I involved. And if I send an I through an R, what happens? We get a voltage drop, and we call it a line loss. So the 100 meters is not the impedance. The 100 impedance is the resistance of the wire. Because it's networking, we're using 24 gauge wire. It's copper, 24 gauge copper wire, but it's still 24 gauge wire. So it's pretty thin wire. Of course, we do that to make the size of the wire small so we can route it a lot better. So yeah, this is 8 wires. It's a 4-pair wire, so it's 4 twisted pairs in here. And that cable's pretty small, right? So we can route this to a lot of different places and get it a lot of places. And it's also thin, even though it's solid strand. The strands are so thin, it still makes it fairly flexible, even though you're not supposed to. Yeah, we don't want to bend this too much. And what we have, and we'll look at that, is called the bending radius. Because if I come over here and bend this too much, I add an inductor, and now we change the impedance of the cable. So all of these cables have what we call a bending radius. If you exceed the bending radius, then you're going to slow your system down. Except Corning makes a fiber, and how they do it, I don't know. But they call it low loss fiber, and they're bending that thing in 90 degrees, and it still don't have any loss. How Corning does that, I don't know. But Corning's leader is fiber. So we're up to Cat 6. My chart stopped at Cat 5. We're up to Cat 6, that's version E. So you can just take the speeds and go up. But Cat 5 cables rated at 20 to 100 megahertz. So we rated at 100 megahertz. Now this is the frequency of the carrier. It used to be that the frequency of the carrier and the baud rate were the same, but not anymore. We have different ways that we can modulate this or put more bits per carrier. And now so even a gigabit Ethernet is still, the carrier is still 100 megahertz. Then we got STP cable. Look at STP cable. It's rated up to what? 300 megahertz. 90 meters. I always learned, I don't know where this chart came from, but I always learned 100 meters without a repeater. So what that means is you can run it further than that, but you're going to have like a switch or something every 100 meters to do what? To receive it and then re-amplify it. But 100 meters, guys, that's 330 feet. If I'm going to run over 330 feet, I don't want to run copper anyway. I want to move to what? Fiber optic cable. So here's some fiber optic. 62.5, 125 cladding is 2,000 meters. 2,000 meters. Multiply that by 3.3. So that's over a mile, right? Single mode fiber, which we don't have, we'll be dealing with this fiber hub. We'll be dealing with this 62.5/2025 fiber. That's the one we're going to terminate. But believe it or not, termination is the same because it's good for 3,000 meters. They've got it, and that's a long way. They was talking about the Russians getting trying to travel around our fiber running under the ocean. They was talking about what would happen if they started cutting the fiber going between the countries. There's no telling how much fiber. So these are Cat 5. This gets up to Cat 7, which I haven't seen. Cat 6 is what we got. Then we got the E version. So they got several versions of Cat 6. So Cat 6 uses 8, but Cat 6 gets us up to 8 pairs. It gets us up to what? So on Cat 5 is rated for gigabit Ethernet. Yeah, it's the E version. I have to go back and look and see what that is. We have a 6E. We have a 6E out now, and exactly what that would mean, I don't know. I've never seen Cat 7 category. It's category, but everybody calls it Cat 5, Cat. Cat 6. Yeah, a lot of people, usually that's what you buy now is Cat 6 cable. I don't even know if you could probably get that. That's got a blue jacket on it.
So different colors, maybe something? Like if you want-
Used to you could get Cat 5, and some of them would be gray, some of them would be blue. But they've got in a habit on these things of start color coding the jackets. But we got so many versions out there. This is especially true on fiber. Fiber, we have so many versions out there that they color code the jackets. So usually multi-mode cable has an orange jacket, and single mode cable has a yellow jacket. Not the conductor, the jacket. See what? Now we got some blue Cat 5 cable, we got some white Cat 5 cable. So it's not true on Cat 5. I just don't know. This is what we didn't get to, is these different ratings. So when we look at the jacket, this jacket says, and it's written on the jacket, if I read this says it's Cat 5E verified UL, 24 AWG, American wire gauge, CMX. CMX is this jacket right here. That's the rating of this jacket right here. And we have different ratings on these different jackets that would tell us where we can run this cable at. So what's the function of the jacket? From the environment, right? You understand? Okay. Not much can do that. So if it's got CMP and it's got CMP, it means it's rated for what? Plenum. We talked about the plenum. What's the plenum? Yeah, the space between the artificial ceiling and the real ceiling. Complies with this, National Fire Protection Agency's UL. Only cables allowed in the space-defined air plenums such as raised floor systems and air. So they say the plenum, if you get in some sure enough computers, I mean, we're talking about sure enough computers, not these desktops, sure enough computers. What they do to cool them is the floor is actually raised, and they run air conditioning under the floor. And then what they do is every time they put one of these big stacks of all these hard drives and stuff, they'll just cut a hole in there, and then it'll blow up right up through the bottom of the drives. That would still be called the plenum, right? Yeah, it's raised up, and all the cooling runs under the floor. Well, that's still called a plenum. The plenum cables must be self-extinguishing and not reignite. They also produce less smoke than traditional PVC cables, and the smokes and fumes are toxic. So if you're going to run cable up in here, or if you're going to run it through that floor plenum, you need to have plenum rated cable, because that's circulating air, right? You understand that? You get all these toxic fumes and that garbage. CMR, this is riser cable. Riser cable is cable, the jacket's designed where you can run that stuff vertical. Yeah, but vertical. Complies with this. UL listing defines for uses in vertical trade applications such as cable runs between floors, through cable risers and elevator shafts. The space cannot be used for environment air, so we can't run it through air conditioning duct, right? Because if it catches fire. These cables must be self-extinguishing and must prevent flames to travel up the cable. So that means even if they do catch on fire, they're supposed to extinguish themselves. And usually flames move what? Up. A CMP, which is what's our CMX, right? Yeah. Complies with these, NAFTA, and also UL. Only cables allowed in space-defined air plenum and raised floor systems and air handling. Plenum cables. I thought we've already looked at that. I went back. CM, CMG, and CMX. These are what? General purpose jackets. Will burn and partially self-extinguish, not used between floors or plenum, air cables, and used in workstations and patch cords. So these are general purpose cables. So CMP, CMX, CMR, CLPs, these are class 2 remote control signals. FPLs, these are power limited fire alarm cables. So I just can't use regular wire in a fire alarm system and still pass code, right? I gotta use a cable that's what? Rated for that. CATV, communication antenna cables, FOP, these are non-conductor optical cables. Conductive optical cables. Conductive cables mean they include conductors in there along with the fiber. Power limited tray cables, network power broadcast cables, BM, BFA. So where's this at? This is identifying where we can use these cables, and these are this information is supposed to be stamped on the wire, on the jacket, along with the gauge. We're supposed to put the wire gauge on there, and we're supposed to put where we can use that cable at. I think your fiber is going to be labeled OFRs, OFNRs, OFNs, OFCPs, OF. So OF means what? So C means copper, O means optical, and then we have different ratings for the jackets where you can run these different fibers. Are we okay? We're okay. This makes sense. And the UTP impedance. So here's impedance. But this impedance only becomes true if you maintain the what? The twist. Within a certain limits. We can keep it out, I think it's 1/4 inch. So when we can untwist them about 1/4 inch and still maintain the impedance of the cable. Because a 1/4 inch on one connector and a 1/4 inch on another, that's 1/2 inch. So that's a 1/2 inch. But you've got to do both sides of the connector, right? Especially these, the RJ45s that we're using, you're going to have to untwist it some. The punch downs, you can pretty much carry those just about out to the punch down. But still, you got that space between where you terminate here and where it picks up on the other connector. This is just a basic look at fiber cable. So, the outside that actually contacts, so this is the jacket. And then normally inside the cable, we have a strength member, which a lot of people call Kevlar, but it might not necessarily be Kevlar, but it has the same, it's called an Armistead, because Kevlar is a copyrighted name, right? You understand that? So it might not be exactly Kevlar, but it actually is like it. And then what we have is we have the fiber, here's the fiber, and then this right here, we don't call this a jacket, we call that the buffer. And we have two types of buffers that we'll look at when we get there. We have what we call a tight buffer. A tight buffer is so this is the jacket, this is the buffer, and this is the strength member, right? Because this is glass. Okay. Now the actual conductor consists of a what? A jacket. Then we have a what? Armored fiber. Then we have what we call a buffer coating. This is going to be plastic. And then we're going to have a what? C is a what? No, something's off, guys.
You got a tight buffer in the buffer.
No, the buffer coating is around the glass itself. The jacket is on the outside. I'll take a break. I'll cut one of these things up so y'all can see it. We have plastic. Plastic has a real short run. It's about 100 meters, about the same as this right here. But we use a lot of plastic in the industry. But if we're going to send it a great distance, so this is a duplex cable. It's got an OFNR, which is a riser cable. It has a loose jacket. So that means the outside jacket is not in contact with the fiber. This is a stripping tool right here that allows us to strip the whole thing. So this outside one, what we do is we just come up here and just put it like that. Then we pull this off. And then this exposes the Kevlar. Then it exposes the Kevlar. You can't cut the Kevlar with special scissors, so we have Kevlar scissors. I don't want to catch anybody cutting paper or anything with this scissor. So this does a real good. It's going to be real hard here because I got it so short. But we use this to cut the Kevlar. This is a tight buffer. Okay. So I'm going to go drop down to my next notch to cut off the buffer. And usually we don't do that much because you want to do it in about a 1/4 inch because it's glass, guys. So you don't want to do it. What we're looking at here, this is the coating. And the coating is strictly in there, the buffer coating is strictly in there to protect the fiber. That's all it's in there for. It has nothing to do with reflecting light. But if we're going to terminate it, we got to get that buffer coating off there. So what I'm going to do is I'm going to go down to the next one. Got to be real careful because you can cut it in a heartbeat. And what we would do, what I'm going to do is I'm going to deliberately, we would do this about a 1/4 inch at a time. We do it at an angle. Can y'all see them at an angle? And then we pull it out. And that's the buffer coating right there. See that white stuff? Now what we're looking at right here is we're looking at the cladding. You cannot separate the cladding from the core. They are one unit. That's what makes it work. The cladding and the core are what makes it work. So basically the light travels down the core and reflects off the cladding. So normally when we show the parts of a fiber, we show them as two distinctive parts, but they're not. We can't see the cladding unless we got a fiber scope. And I'll show you we have a fiber scope that we can look at this. Unfortunately, our dummy plug is clogged up and I can't unclog it. But what I want you to do is, when I pass this around, now don't poke this in your eye. Don't look at it. This is glass, guys. Glass takes a long time to corrode, right? So if you get this in your eye, you're going to do mess up. But what you're doing, you're seeing the buffer coating right here. You can see where it ends right here. And then this right here, you're looking at the cladding, and you can't see the core. The core is inside the cladding. Now, what's so nice is the cladding, not only it gives us two functions. It's what's causing the light to reflect back in the core, but it also gives us the ability to set a standard size. So this is 62.5, so that means the core is 62.5 nanometers. And the cladding is 125 nanometers. So if we look at single mode, it's going to be like a 10 nanometer core, but it's going to be 125 nanometer cladding. So if I look at single mode and I look at multi-mode, I'm not going to be able to tell them the difference because I'm not looking at the core, I'm looking at the wire. I'm looking at the cladding. And they look exactly the same thing. It's the core that changes sizes. And that's the parts of a fiber. That's tight buffer though. So what we mean is that inside buffer is actually in contact with the buffer coating. It's in contact with the buffer. A lot of people say it's in contact with the cladding, but they don't know. That buffer coating's on there, right? And the buffer coating is on there for what? For protection. But when you terminate it, you got to get that buffer coating off because your connectors don't handle the buffer coating. They handle the cladding. No, these tools right here, if you use them right, now notice for one thing, when I cut it, I didn't do like this. I stripped it at an angle. You see I had it at an angle. So the blade is not going to hit this. If it does hit, it's going to hit it at an angle and just bounce off of it. It's not like copper. So yeah, you'll never see me come up here and do this and sit here and do that, right? You understand? So notice when I did the outside buffer, when I did the tight buffer, I did my stripper at a watt, at an angle. And when I did the buffer coating, I did it at a watt, at an angle. And then we'll come back, guys, and we'll use alcohol to clean it off. Syringe grade alcohol. You don't want to use regular rubbing alcohol. You use what we call syringe grade alcohol, so it's really pure. It's at least 91% alcohol. So clean it. You don't clean it. And it squeaks. We'll show you that. But you can tell when it's clean because it'll squeak. But that's just the makeup of a fiber, a standard glass fiber. Plastic is a little easier because we cut plastic and then we can sand it down to get a nice flush surface on it. But plastic is Plastic is a lot cheaper, but it's got a lot more attenuation to it. But it's not designed to run over long distances, right? And now one big advantage of fiber, it is impervious to EMI. We can set off a nuclear blast or one of these big EMI pulses. It'll tear copper up, but fiber don't care. Oh yeah, we can run this through anything. We can run this through any environment. So to run the network, so you can see the orange cable. So to run the network from building A, which is where all the main network stuff's at, it's in building A. They ran it through here. What did they run? They run fiber. For one thing, they had to go outside. Copper don't. I don't want a communication cable that's not shielded real well to go outside, right? Because why? What might we have tonight? Thunderstorms. Yeah. They was running network over in A building, and they couldn't get through the firewall. So what they did is they ran it up through an air vent, which they shouldn't have in the first place. Run it across the top of the roof and ran it back down. So instead of going through the firewall, we had a lightning storm come through, and they blew out the network cards in the whole room. That's a true story, because they ran that copper wire. Huh? No, we did it. That's you gotta imagine when we first started networking, we did everything ourselves. Our department has had our own network since day one. I mean, as soon as we had the capability, we ran a bus topology. So you go over there in A building, between all our classrooms. The whole second floor used to be ours before we split up into different buildings. There's coax running all through there. Yeah, I got to put a sleeve in it, and then you got. Well, they do that. They do that now. So they came in and had the whole thing wired. So the whole college is wired now, even though, and wired is always better than Wi-Fi, right? No, Wi-Fi. You pay for 100 megabit. You pay for 100 megabit Ethernet coming into your router, and then you hook it up to Wi-Fi and you drop that sucker down to 10. So if you want that 100 megabit, you don't go Wi-Fi. You do what? You do hardwire. So yeah, all the stuff I'm going to do at house, I go to my main computer. My wife calls it my command center. Command center, and I do all my stuff in there. Now I only have two desktops in there, and then. Yeah, but you could go Cat 5 and Cat 6, but you don't want to go Cat 5 to Cat 5 to Cat 3, right, or something like that. So. Yeah, and to get the correct impedance on these cables, I think the minimum length is like 3 feet. So if you cut them shorter than 3 feet, then the impedance is not going to be right on these guys. So that's why you don't want to make a network cable that's wide. So this is a network cable that we made for, Yeah. Coax is, I don't forget what coax. Coax has a minimum distance also. Let's get into our next lab. So everybody okay there? And I'll try to upload these things. This one won't work if it's up there, but all this. Yeah, but this guy don't. The animation don't work. But that's what we're trying to show you here: the importance of what impedance matching. Even though we use resistors, because y'all understand resistors, but you got to understand if I put AC on those coils and those capacitors, then we set up what we call an impedance. Instead of that being arbitrary, they do what? They set the impedance of the channel. They set the impedance. And then if you set the impedance, they know what to do what? They know what to match to, right? So I know the phone system. They run twisted pair cable if they're not running fiber. Fiber, we're not concerned with impedance because we don't have R and we don't have X. We don't have all that stuff that we run into in copper. So the phone system uses twisted pair cable. Why they use twisted pair cable? They use for what? To set the impedance of the system. We got one. I think we showed y'all that one. But this is where we was working on. I knew for some reason that we had skipped over that. I don't know how because I could have swore I went into that with you. And we were looking at copper installation, right? No, we have awful network here. It's not us. The main connection is done on the Birmingham campus. So a lot of the stuff we have to do has to ping over there before it comes back, and it's awful. So we looked at this, right? We talked about conduit. We talked about raceways. We looked at pulling. I did add this, by the way, today. These are fish tapes. Everybody seen those? So they're not easy to use. After a while, you learn how to do them. You see people trying to pull that out of there. So you got to feed it out. And then we talked about, I found this too, the pulling lubricant that you can buy. You can buy this down at Lowe's. You can buy it in big old buckets. You can buy it in tubes. We looked at tension. These are some stuff I found too. These are tension gauges. So you can buy tension gauges to make sure you don't exceed the pulling tension of the cable that you're pulling. This is pretty neat because what you do is you route the cable through here, and then how much force it puts down would measure the pulling tension. This guy right here, you would have to be careful with pulling because once you got to the end, right, you understand that you'd have to do something with that. These are your bending radiuses, and this is what's important, especially on communication cables, because that when you bend that thing too much, you add these things we call inductors, which means you change the what? The impedance of the cable. So all these communication cables give you a bending radius. So Cat 5 cable, the bending radius is a multiples of 4 times the diameter of the cable. So you'll understand that. So what I would do is I would measure this diameter, and then I would multiply by 4, and I would not exceed that bending radius. Y'all understand bending radius, yeah? Does that make sense? I think this is a pretty good picture right here. What you would do is you just draw vertical lines, and then you would measure this angle, right? You understand that? If you could. UTP is 10 times the diameter. Multiple pair coaxial is 10 times the diameter of the cable. Fiber optics is installed different types of cables. We'll look at premise cable and interconnect cable, outside plant cable. So we'll have to get it when we get into fiber. We'll look at these different cables. By the way, we call this a cable, even though we call this a cable. Even though it's got one conductor, we call this a cable because it's got multiple layers, right? So we use that thing. It's kind of misleading. A lot of people say a cable has one or more conductors, but we also use the term for conductors that are built on multiple layers, right? Separation. This is separation. So you got to understand when you get by these big AC lines, they generate a lot of electromagnetic interference. So we need to make sure we separate these things. So it says on a 2 to 5 kilovolt, we need to separate it at least what? 12 inches. Now over 5, at least what? 10, 20. If it's shielded though, we can get it pretty close, right? You understand that? Okay, so this is where we want to get to because these are our next labs. These is where we start splicing. So right now we're doing splicing and termination with solder, right? What we're going to do here, we're going to do splicing. We're going to splicing and termination with crimp connectors. And we got tons of them. And I think this is where we left off, wire nuts, right? Everybody okay on wire nuts? And this came off of something, but actually what you need to do is you need to get a chart because I think I showed y'all this, right? You get different combinations of wires you can put inside these things. So these are yellow wire nuts. Looks like I closed out my camera. But we passed it around. Is everybody okay? Or we can pass it around again. Keep going by it. Okay. So actually, these says you can put 22 to 18 gauge in a wire, 14 to 10 in a yellow. But what you need to do is you can combine different gauges and put different combinations inside that. These are what we call split bow crimps. And we don't have any of these that I know of. I don't think we've got any over there. Can you see how these work? So these would work on stranded because the strands can't go anywhere, right? You understand that? Huh? Yeah, also in your battery, if you buy the terminals, you can buy the terminals on your battery and replace just the terminals on your battery. They're usually going to be something like this or something like this, right? These are compression or crimp splices. Some of them are not insulated, some of them are. The ones we have are insulated. And then they'll have a jacket around them. And then the insulated ones, the jacket will actually indicate the gauge of the wires that you can splice together, right? And we call these butt splices. Why do we call them butt splices? Yeah, the wire actually butts together. Now, most of the people don't quite use these right, and we'll try to show you how to do that. What you want to do is I already had that one selected. Yeah. So what you want to do is you want the insulation to go in the very end of the splice. And then what you're going to do is you're going to crimp it twice. You're going to crimp it in the center, and this will crimp your conductor, right? And then you'll clip it out here on the end, which will be right here. And your insulation should be barely up in there. Because what you want to do is you want your insulation to give you the support for the splice, right? So you basically get multiple supports for the splice. What's that? Squeezes it, right? So you got two crimps that when you look at a crimping tool, you're gonna have two crimps on it. One of them says for the what? One says for the wire, the other one says for the what? Insulator. So we're gonna crimp the wire with this guy. Now, what you got to notice is these guys are done in a tube. And they're rolled. So that means they've got a seam in them, right? Y'all understand what I'm saying? Yeah, the metal is in a seam. It's got a seam in it. And a lot of people do this wrong too. No, the one that punches through, you want it away from the seam. No, because if you do that, so what you do is you got a seam right here. Now what you want is you want the round side to be on this side. Because if you don't, you go into that seam, it's going to separate. And then what you want to do is you want to push that barrel down into this side right here. So what happens is this actually forces the seam together and don't let it split apart. If you flip that around and you crimp on the seam side, then it's going to spread the seam apart. Guaranteed. And then what you do, so y'all see what I was talking about, yes or no? So the first thing you do is you look for the seam. Y'all won't be able to see it, but I'll pass this around. You can't see it there, but there's a seam here. So when I place this in the crimp, I want to put my seam, I want to put the seam on the round side of here, and then the part that's not on the seam, I'm going to put over here. No, this is the insulated bus bar.
I'm talking about on the front foot, you want on the other one without the thing.
No, one of them is to crimp the conductor, which is bare. The other one is to crimp the insulator back here on the back.
Oh,
Okay, you understand? So you got two things you're crimping. You're crimping the wire. Insulator. So this is the bare wire. So these guys, you're going to have to strip them, and we'll give you the links on how to strip them. The first thing you're going to do is you're going to find that notch in here, right? You understand? And then yeah, but if you ever look, you see it's flattened out and it spreads apart. You understand? So what we do is we put what? We put the round side. We want to put that where it meshes right there. We want to put it on the round side and crimp on the other side. You understand that? Charles, you understand that? This is a compression. We got a sort of a compression. And I didn't bring it. Here's where they're using aluminum. I think we talked about this. Oh my God! Did I show you that aluminum crimp? They put the antioxidant in there. So this is mixing copper and aluminum. Yeah, see, it just broke the aluminum. It broke the copper down. Copper just corroded. This is what we call dissimilar metal. You can mix copper and aluminum, but what you have to do, if you're ever going to splice aluminum, so this is the crimp splice right here. And what they've got is they've got that antioxidant paste inside here. It looks like grease, guys. And what that does is it prevents the aluminum from oxidizing. Aluminum has we got two problems with aluminum. One's it's got a pretty big coefficient of expansion. So that means when it gets hot, it expands a lot. So aluminum is constantly trying to work itself loose. So we need to get a really, really good crimp on that stuff to keep it from breaking loose, right? And the next thing what we want to do on aluminum, if it's going to be exposed to the atmosphere, we need to put that what on there? We need to put that antioxidizing compound. But this is a crimp splice. Now some of these crimp splices, these are hydraulic, or you'll see them, they'll have big long handles on them. Or they'll have a hydraulic one where they put it in there and they pump it and crimp those things. You're not going to crimp those with a standard crimper, that's for sure. It's just like this. So this is a crimp terminal here. So you're going to have a special crimper to crimp this guy, right? You understand that? So this would be a crimp terminal. I'll show you a video on the splicing high voltage and medium voltage cables. But I can show you a video on that. Let's see what else we got. I think this is all. I think the next thing they do is high voltage cables. Oh no, these are compression. So one advantage that solid strand has over stranded is that we can just wrap solid strand around screws. So solid strand is easier to terminate, right? It's easier to splice. What can we do with solid strand that we can't do with strand? You still end up with a pretty strong splice. Just twist it together, right? You understand? Twist it together real good, right? Or put it in a wire nut. A wire nut makes it really, really good. You can't hardly pull that apart. So the big advantage of solid strand is that it's easier to terminate and easier to splice. But it's not flexible, right? The biggest advantage of stranded is a lot more what? Flexible, but it wants to bird cage all the time. It wants to come out of those spirals. So that means usually when we start getting with stranded wire, we're going to have to terminate it with terminals, either solder terminals or what? Or crimp terminals. I made my go, even though I'm sitting in my chair, because I use my hand a lot. So this is what, these are different crimp tools. Of course, these are the ones that we're using. We have some that flatten crimp, but we don't want to do that. The best crimp that we're going to do when we crimp the wire is to do one that's got this notch in it right here, right? And that gets the best crimp on the wire. And then we'll move back to the insulation and crimp the insulation. Are you okay? Make sense? Everybody okay? So cutting that to the right length is really important. So what you need to do is you need to dry fit it, right? Of course, over time you'll learn the lengths, and I think I give you the lengths. But you'll learn it over time, you know, if you do a bunch of these. But to start off with, you need to strip it, you need to twist it together real good, you need to put it in there. And if that insulation doesn't go up into that insulation just a little bit, you don't have to do very much, right? You understand that? Then you need to do what? You need to clip it off a little bit. Right? That makes sense? These are colored insulators, and we got all type of thermals here. Good gracious. I mean, all types. We got the blade types, and we got the males and the females. We have these types that plug into each other. We got these guys that are used to terminate under screws that we could use. We got ring types. We got fork. Yeah, it's got the fork type. I don't have that in there. The fork type, you got to be careful with those because those will want to back out from under the screw on them, especially if you put multiple terminals on the same screw. The ones, some of them will try to back out of them. What you need to do is notice you got to. People won't do that too. You'll end up with a high side and a low side. So it'll come up like that. But some people think you got to put this side down, but you don't, right? You understand? So what you probably need to do if you're going to put two of them, put one of them high side down, and the other one high side up, and you get a lot better connection. But you can bend them, you know. They're just don't bend them. Don't bend them like that; they'll break. But you can bend them at an angle, you know, up. You can't bend them sideways, but you can bend them at an angle to get a better connection. No, I don't have a fork type. These are the color codes, by the way, so they're all color coded. So we have yellow, standard yellow, the small yellow, and you can tell the difference, guys, if you understand gauges. So yellow is used, and they repeat, right? You understand? So we have these guys, which are the ones we got. So a small yellow is from 26 to 22. A transparent from 22 to 20. It's not actually transparent. It's kind of translucent. Blue is what? 16 to 14. A yellow is a yellow black is 16 to 14. Then you got a big yellow. So they've only got what? Just very few colors, yellow, red, and blue, and then they keep repeating, right? You understand? So it's up to you to know that this big old yellow right here, which would handle a number 4 gauge wire, is not this yellow right here, right? You understand that? Well, this is a yellow. You know, you got a hole in it that big in the back, and you say, well, I'm going to put these wires in there, right? Y'all understand that? So they keep repeating. The only one that don't repeat is what? It's transparent. But yellow, blue, red, yellow, blue, red, yellow, red, blue, yellow, red, blue, yellow, red, blue. Right? These are compression terminals. I think this is one of these guys right here. So these guys, you have a special tool you're going to crimp with that thing, right? Usually these guys have multiple fingers on them. They come in. Depends on what they are. A lot of them will crimp in a octal type shape. Did I bring one of those out here? Well, this is basically a compression type crimp.
Is that one connected right there on the wall? big wire.
Yeah. Can't see. Yeah, we can probably.
So you ain't gonna use this on that.
No, you're not gonna use that. But you have different tools for different gauges, right? You understand? So that goes down pretty small, but it would get up to a pretty good size wire. And you learn real fast where the release is at. It's got a little release. Well, no, it's got a release on it somewhere on the side, yeah. Yeah, you learn where that's at real fast. Now that's fairly small for a compression type crimp, right? Yeah, it's got a little thing on the side where you can release it without going all the way down. Because what would happen, you get it on the wrong gauge and you get it started and you can't crimp it. Has that ever happened to me? Yeah. So these are different compression tools. And of course, this would be the hydraulic ones, right? Compression configurations. The one that we have is either this one. The real small ones is the round ones, but the larger ones is this hexagon. Yeah. On this one, the larger one is the hex type. These are both the terminal lugs. Everybody okay here? Most of these are pretty straightforward. We do have a torque. We do have, and I'll show y'all this too. One of the high voltage splices. When I show y'all the video, that's what you do. How do you don't have a torque wrench because the splice is not made to come off because it's a high voltage splice. So what you do is you tighten it down to the head breaks off. And when it breaks, you know what? You got it to the right torque, which is pretty neat. And then you put a little compound in there. So you see that used sometime on these splices that are not intended to be what? Taken off. Let's come up here and now I don't know if the video is going to record. I have it set up to record my speaker, but sometime it don't work. But I'll post it up there on Blackboard when I get time. The problem I have, I think I've told you about my T2. I'm on campus 35 hours a week, and I'm in class 30 hours. I got 5 hours to do everything. Every Friday since T2 started, I've been in meetings. So my Friday has been the pits. Huh? Yeah, but it's part of the job. Okay, so ET, this, graphics, videos, copper, high voltage, medium voltage cable construction, and then this is two methods 3M's trying to sell. One of them is the old method using the heat shrink method, and another one is using what they call the cold shrink, which is what they're trying to sell. So this is basically a commercial.
Hello, and welcome to 3M. We're the innovation and practical solutions company you have come to trust.
When you're in control of the volume, it might work.
For over 100 years. You'll find innovation and practicality in everything we do, including our solutions for medium voltage splicing and terminating. This is an interactive module, so please click the arrow below to begin. This presentation contains examples for general practices only. For specifics on individual applications, see the 3M datasheets and technical illustrations. It is the responsibility for the users to test and verify the performance of these materials in the final application. This is the first module of the medium voltage splicing and terminating series. The purpose of this module is to familiarize you with medium voltage cable construction. This knowledge can then be used when splicing and terminating.
What's medium voltage? What's high voltage? What's low voltage?
100 to 1,000 volts. That's low voltage.
Well, it all depends on what we're talking about. Alabama Power considers high voltage and low voltage completely different than what we consider high. So our house, we say low voltage is 120, high voltage is 240. Alabama Power says, well, anything above 30,000 volts is medium. Between 30,000 and 57 or 75,000 is medium voltage. Anything below 30,000 is low voltage, right? You understand? Because they're power company. So it all depends. If you go out to U.S. Steel, their highest voltage out there, I think is, 660 or something like that. That's what they think is what. They call that high voltage. So what's high voltage all depends. So usually when we talk about this, it's called transmission, and we'll look that up and see what these voltages, what they define these voltage levels as being.
By the end of this module, you should be able to describe the function of the 6 layers of medium voltage cable. Medium voltage cable is electrical cable with a voltage rating of 2 kilovolts to 46 kilovolts. Any cable with a voltage rating higher than 46 kilovolts, such as 69 kilovolts, is considered high voltage cable. Medium voltage cable is what is commonly used throughout electrical distribution systems, power plants, and industrial facilities, such as oil and gas production facilities. It is also what is used to bring power to our neighborhoods, schools, malls, and offices. There are 6 distinct layers in medium voltage cable. They are conductor, strand shield, insulation, semiconducting layer, metallic shield, and jacket.
We looked at that, right? We talked about that. In fact, that's what we looked at over here. And what's the function of all those layers besides the insulator? Huh? But the metal layers, the semiconductor layers, what are those in there? To equalize the pressure around the cable, right? Understand? To make sure, the electrical pressure around the cable to equalize it so it don't try to concentrate to one side, right?
Each of these layers are critical to the cable system. You can click Next to continue, or click on a specific layer to jump to an explanation. There are 2 basic types of medium voltage cable, single conductor and 3-conductor cable. Single conductor cable consists of 1 conductor per cable, while 3-conductor cable has 3 individually insulated and shielded conductors. The conductor is the heart of the cable, as this is the portion of the cable whose sole purpose is to carry current.
Now notice on this one they actually added an armor coat, right? And then down below that is basically the same.
Strands that make up the conductor can be made of either copper or aluminum. Copper is generally used for industrial applications, whereas aluminum is generally used for utility applications. Conductor configurations are concentric, compressed, compact, or solid. The next component is the strand shield layer of the cable. This is a semiconductive layer of the cable. Its function is to shield the cable insulation from any air that may be surrounding the conductor strands. Without this protective
what would happen is, so this is basically to prevent the cable from arcing in there, right?
Semiconductive layer, the air will ionize, resulting in partial discharges. This can deteriorate the cable insulation to the point of failure of that cable. The purpose of the insulation layer is to contain the voltage of the cable. This layer can be made of materials such as EPR, or ethylene propylene rubber, or XLPE, or cross-linked polyethylene. Insulation has a standard operating temperature rating as well as an emergency operating temperature rating. The next layer is the semicon layer of the cable. The function of this layer of the cable, somewhat similar to that of the strand shield layer, is to shield the cable insulation from the air that is between the cable insulation and the metallic shield. The metallic shield is the conductive, metallic component of the cable's shielding system. It serves many different functions. It contains the electric field within the cable, provides symmetrical radial distribution of voltage stress in the insulation, limits radio interference, and reduces the hazard of shock. It also serves as a return path in the event of a short circuit, and for concentric neutral cables, it provides a neutral return path. The metallic shield must always be grounded. Shown are common cable types. Tape shield cables fulfill the 6 different functions of a medium voltage cable in 6 different layers.
That was it.
Wire shield cables have the same.
Oh, that, I actually opened the wrong one, guys.
3M standard cold shrink tape electrode joint offers a viable cost-based alternative to heat shrink cable jointing technology and allows for a reduction in installation steps. Unlike heat shrink alternatives, a molecular permanent set ensures constant radial pressure is exerted on the cable for the duration of the cable joint's life. Unlike the individual layers that are necessary for a heat shrink joint, which must be allowed to cool sufficiently before the next layer can be applied, 3M cold shrink splice bodies contain all the necessary layers in one component. Any additional cold shrink layers, such as our outer protection tube, can be applied immediately. Scotch 13 semiconducting tape is used to overtape the connector. Layers are applied tightly around the connector, overlapping the primary insulation on each side. This stage replaces the need for a heat shrink tube used in competitive heat applied alternatives. 3M invented cold shrink technology over 30 years ago. Our cold applied products utilise the unique cold shrink delivery system, designed to make cable jointing, insulating, termination and abandonment as simple as possible. Compared to heat shrink alternatives, there is less chance of damaging XLPE cable material, less room for jointer error, and no cooling time needed before energising. It is easier to use in enclosed areas, and there is no requirement for special site permits.
Look at the cold string. So what it's got is it's got this, looks like a Teflon spiral going through, kind of like a spring. And when that guy comes up here, he'll just pull that thing out and it'll collapse back on there.
In a number of applications, time-saving benefits of cold shrink can be considerable, thus lowering the overall installation cost. Additionally, many of the joint bodies are comprehensively factory tested before released, something simply not possible with heat shrink due to its material nature. Finally, as a result of continuous development and refinement, only 3M can offer you such choice in cold shrink technology in terms of product cost and flexibility in its application.
y'all think? Makes y'all want to go out and splice some high voltage. Of course, you know that's why we can't do that, because that would be very expensive even for the splicing kits. So the splicing kits are not cheap. And we got that one because they did something wrong. So that's why we got that one. So there's something on there which I can't find, which was done wrong, and they had to do what? They had to cut it off and re-splice it. So guys, I think that's it. So, flex line shield. By the way, on these high voltage cables, what they do is they have special types of things that they put on the end. Y'all might have seen it before. That prevents it from doing what? Arcing back over the insulation. And I know y'all have all seen these guys, right? These insulators that's on these high tension lines. Terminal blocks. Now we got one more thing to do. Everybody okay on terminal blocks? Make sure you okay there? Wire and connect terminal blocks. Screw type terminal blocks. These are used a lot on PLCs, where you, when you insert the wires in there, all you have is the screws on the top. And what's nice is that you can use either solid or you can use stranded wire in those. This is what we wanted to get to. These are RJ45s and RJ11s. RJ45s are what we use for Ethernet, and RJ11s is what we use for wired telephone systems. And these are crimp terminals. We have two methods we do this. The first thing we do, so if we was to take these plugs out over there on the wall, what we would do, we would see a bunch of these guys right here. And these are called punch downs. So we have two punch downs. We have what we call a 66 block, which is used for a lot of part. We still use these for bringing like the phone company into a building and then splitting it up to individual phones. We use these 66 punch downs. So this is a punch down block right here. So what we would do is we bring the cable into one side, into this terminal. This comes up into these punch down blocks right here, and then we would punch into these depending on which route we wanted to go. Now this is going to be twisted pair cable, so the twisted pair cable would come in on the other side, right? You understand? And it would come through these grooves and go into this punch down. So what we have is this is a punch down tool, and this is a changeable punch down tool. And so what we have is we have this guy that's in there. This is for a 66 block, which would be this guy right here. The one that I passed around is what we call a 110 block. So what we have here is we have another side that would come in here, and then this right here would be for the 110 punch down. And you'll see 110 on here. Somebody's lost the. So on the 66, we're set on there now. What we would do, when you don't strip the wire, which is so cool, what happens is the block itself has blades on it that's smaller than the wire gauge itself. So what it actually does, it actually bites. Can y'all see the way it gets narrow as it go down? So it literally bites into the insulator. So we don't have to strip the insulator. We'll find out that this is true. This is true on our network cables also. So this is a stripper that we use for this because we don't want to cut this with a knife, because what we want is we want it to have a perpendicular cut. So this is a stripper that we use. I'm gonna cut some of this off. These are a pair of cable cutters, by the way. You get different sizes. I've seen cable cutters that was actually hydraulic, so so all we need to do is strip this jacket off. So we come in here, lay this down in here, and all we have to do is spin it. And what we want to do is make sure that it don't nick the wires. So if I see it that it nicked the wires, then that means I need to come in and do what? Adjust the blades out a little bit. Everybody okay? Does that make sense? Now what we would do here, and this is the strength member right here. So we can cut this off. This, you don't need Kevlar's on that. This is just usually nylon. So you can just cut it with a standard pair of cutters. And then we would bring this into the side. And then we would get what we want to do, and then we'd untwist it just enough to make our connection. Then what we would do is we'll come in here, we'll lay it in the groove right here. And then we take our punch down right here, which is a 66 block. And when you notice the punch down, it's got a blade on one side and it's flat on the other. But what we want to do is we want to make sure we turn the blade away from toward the end that's sticking out. See what I'm talking about? Yes or no? Okay, then we come down, we push it down. Oops. We got to get it into the groove, Rich. So we started into the groove, right? And then we come in, put the blade away from the conductor toward the end that's out. We push it down, and we hear a snap like that, and it automatically does what? Pushes it down into the block and also cuts off the end that extends out. And this would be for the 110 for the 66 punch down. Everybody okay? Punch down block? That makes sense? And you'll hear some people do it. You have to do it a couple times. Normally you don't have to do that. By the way, what's so nice on here, so it actually strips that, and if you need to take it out, you can just grab it and pull it back out. So you don't have to strain relief this, right? You understand? Because you can pull that thing right back out. If I was going to do the 110 punch down, it's a little different in that it's still got the blade on there. But when you look at it, it's got the blade on this side, so this is where you're going to cut off the end away from the conductor, right? The end that sticks out, and then this will go on the other side. We'll come in, we'll put it in our punch down tool, and then the 66 punch down. This gives you the color code for, and we're going to talk about that. We got two ways we can wire this. We can wire it in what they call a 586A or a 586B. So that means, okay, if I want to wire it in a B, then I would wire this side like this, and this would be the color code I would use on this side, right? Understand? If I was going to wire it for an A, then I would use this color code on this side, and then the A color code on that side. Everybody okay? We'll talk about the A and the B in a minute. Okay. But what we do on this, and I'm not going to pay any attention to color, is we're going to take this jacket and we're going to run it up this groove. Because what we're trying to do is we're trying to minimize the number of twists that we get out of here, right? You understand? And then what I would do is I'm going to take it, and I'm not going to worry about the twist right now because I'm just demonstrating. And what would we do? We'd come up here and we'd lay it in the groove. Can y'all see me? I'm sorry. So we come in the center, so our wires are going to come out this side right here. We lay it in the groove, then we take this guy and we want to point this blade toward the end that we want to cut off, right? Then we'll come in here and we'll set it down on there, and then we'll push it, and then what would it automatically do? It didn't cut mine off, so I'm going to have to do it more than that. And then it'll do what? It'll cut off the end for us. And what it does is it pushes it down there, and you see how it got the name as a punch down block. So I guarantee you, if we took this cover and pulled these gray boxes out on the side, these little punch down, these 110 punch down blocks would be in there. Now we have two ways we can wire this. We can wire it as a 586B or a 586A. Now we have two ways that we can wire this. In communication, we have what we call data communicating equipment, This is what the information flows through to get to one point. And then we have what we call DTEs, which are data terminal equipment. Data terminal equipment is what's actually doing the termination, right? Y'all understand that? So this is a switch right there. What would that be? That's going to be a DCE. It's what information flows through. It's not where the information goes. A printer would be a DTE, right? You understand? A computer would be a DTE, right? You understand? So if I'm going to hook, this is standard. And what we want to do is we want to do it according to the standard that we use, right? So the color code we have for the 580, and I need to bring that color code over here and show y'all. And after a while, when you deal with these cables a lot, you would learn them. I thought I had the color code on here. There's a printout on top of the workbench in here. If you're sitting at the workbench, you'll probably see that. So we're looking for the 586A, because I hear you there. So these Cat5, these network cables have a standard color code. We have a solid wire twisted with the same color with white. So we have an orange-white, we have an orange-white pair, we have a blue-white pair, we have a green-white pair, and we have a brown-white pair. Everybody okay? Okay. So this is the color scheme for a 585. I said 586. I got it backwards. 568 watt A and B. Everybody okay? So this is the color code you have to match, and what they do is they actually split the pairs up. But when they transmit the data, they transmit and receive on a pair. So you can't make this up. You just can't choose your own color code, because you might be transmitting and receiving on wires in different pairs, right? You understand what we're saying? So the 568B, this is for what we call a straight through cable. A straight through cable is when we connect a DTE to a DCE. So if I was going to connect my computer over there, I would use a straight through cable. Y'all understand that? Does that make sense? If I was going to take my computer and connect it to another DTE, then we're going to have to roll the transmit and receive. So 2 wires is used to transmit, and then 2 wires are used to receive. So of all these 4 pairs, we're only using 4 wires. We're using orange, white, orange, and green, white, and green, white, green. Orange, white, orange is transmit. Green, white, green is receive. So that means if I took my computer and wanted to connect it to another computer, and I use a straight through cable, my transmit would be going to the transmit of the other computer, and my receive would be going to the receive of the other computer, right? You understand? So if I'm going to hook 2 DTEs together, then I got to use what we call a crossover cable. If I'm going to hook a DCE to a DTE, then we use a what? A straight through cable, right? You understand? So a straight through cable, we wire both of them 568Bs. Now why they didn't use the A, I have no idea. If we're going to wire a crossover cable, we're going to wire one end as a 568A. The other side we're going to wire as a what? A 568B. Y'all understand? So this cable right here is designed to hook this computer to that PLC back there. That PLC is a computer too. So both these guys consider themselves to be what? DTEs. So by George, if I hooked up a regular cable to that guy, I'm not going to be able to communicate with it, right? You understand? Now, if I was to go through a switch, then we're okay. We'd use all what? Straight through cables. You understand? So this is a crossover cable. And this is a crossover cable. So if you looked at the color code on this one of them is going to be orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. If you look at the other side, it's going to be what? Green, white, green, right? Orange, white, blue, right? I know the A, B. but it would roll the what? The green and the what? The green, the orange, white, orange, and the green, white, green pairs are what drove. And the blue stuck in there, right? So if you look at this guy, I look at this, it's orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. I look at this, it's green, white, green, orange, white, blue, blue, white, orange, brown, white, brown. So this is the what? This is a crossover cable. So I could take two computers. I could take another laptop and I could hook them together and they could communicate with each other. Right? You understand? Setting up what we call a peer. I could take this and hook it up to that right there and it'd be okay. If I took this and hooked it over there, I'm screwed. Right? Because this is for a what? Straight through. This is for a straight through cable. Everybody understand that? So these color codes, you're okay? Now let's see if we can splice them. So this is and most of y'all have seen these. If you dealt with networking at all. So these are called RJ45s. I can't remember. Anybody remember what the RJ stands for? I should know that. But it's just a standard. It doesn't mean anything about the number of carat. It's just a standard that they came up with, and they was just on number 45 when they came up with this guy right here. So this is what we call an RJ45. It's set up for 8 conductors. And of course we use twisted pair conductors. These are crimp connectors. Which means what? That means you crimp them with a special crimp tool, right? When you get these things, and I'll pass it around, if you look at the blades out here, they actually protrude out. So they're actually out a little bit. And what you do is you don't strip these wires. I've seen people do that. What you do when you crimp it, it takes these guys and pushes them into the conductor and actually cuts through the insulation and makes your conduction that way, right? So you just strip the insulation in there. What you're trying to do is you're trying to maintain it. And when you crimp it, it's got a crimp for the jacket. And this gives people problems too. They don't get the jacket under the what? The crimp. And now your conductors are handling all the stress. One of the biggest problems we have is this little old plastic tab being broke off. And what does this plastic tab do? It locks it into the female connector, right? You understand? So what we need is we have these little protectors that they come on, and what does it do? It protects that little latch. And what I like about these, some of them are actually epoxied on there. What I like about these is sometimes it's hard to push it down. What I like about these is you can pull it back and disconnect it and then and then slide it back over to protect it. So I like these. I like the covers that we got. So this is what we call a crossover cable. This is a crossover cable, but this is a shielded twisted pair. Orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. This goes green, white, blue, so this is a crossover cable. So this is what Siemens gave us with our new PLCs. Crossover cable. And of course that's shielded, that's STP, that's industrial Ethernet cable right there. So what we would do is we'll come up here and everybody okay so far? So what I would do is I would come up here and I would cut off a section of the jacket with my my jacket stripper, right? Depends. We usually cut off a lot. And why I cut off a lot is that what we're trying to do is we're trying to get this thing out of these twists. So I usually cut off 2 or 3 inches. And then I'll come up here and I'm going to take these guys and I'm going to untwist them. And I'm going to untwist them all the way back to the jacket. And then what I'm going to do is I'm going to take my crimp tool or something that's got a rubber handle on it. And once I get them all untwisted, I'm going to use that to get the twist out. Okay, you understand? So we strip off enough so we can manage this thing and untwist these. If I strip it down here, it's going to be hard to get the twist out of the section that's supposed to go into the individual little slots. So I can come up here and just do untwist these. Well, we're going to cut off all this. Yeah, if I was to crimp it down there, but I've seen people do this. I've seen people crimp with this like this. So what we do now is usually I get something like this, and then I lay this on here, and then I come up here and start pulling on it to do what? Straighten it out, because this, if you got it twisted like that, it's not going to go into it. Now, when you cut these, this is where it becomes critical, where you want to cut these to a certain length. So y'all see how I'm doing this? I'm just doing this to do what? Straighten it out. Now, on our crimp tool, where's our crimp tool? And the crimp tools that we have, you can either do RJ11s or you can do RJ45. Most of them are. So here's the crimp tool. Now these are the blades that are going to insert up there and actually push those conductors up, push those blades up in there. But what's nice, it's got this cutter right here that allows me to come and do what? Cut this off to the length that I want to measure. And I'm not going to measure this out. So what I would do right now is now I've got these things out where I can handle them. So what I'm going to do now is I'm going to rearrange these suckers in the right order, right? You understand? So let's say we're going to do a B. What's a B?
Green.
Orange, white, orange. Wait. But see, now I got plenty of stuff to work with. You cut these things off when they get down to the right size to get into that insulator. It's hard to get them in the right order. So orange, white, orange, green, white, blue. Green, white, blue, blue, white, green, brown, white, brown. And this is fun, guys. So orange, white, orange. I had orange, white, brown. Orange, white, orange, what? Green, white, blue. Blue, white, green. Brown, white, brown. Now, once I get them into the right order, I'm going to get them really close together. So I've got them in the right order. I'm going to come up here and double check this. Orange, white, orange. Green, white, blue. Blue, white, green. Brown, white, brown. And then what am I going to do? I'm going to measure that out. I'm doing this by. Okay, then what am I going to do? I'm going to put it under here and do what? And I'm not going to let this go, guys. So I got it in the right order, right? I'm not going to let this go. I'm going to come up here and I'm going to clip it off. Don't clip your fingers. Oh, wrong side. I'm still okay. I think I might have just screwed up. That's okay. Okay. Now I got them cut off. Now what I'm going to do? Notice what I'm doing. I'm still doing what? Holding these. And then I'm going to take my connector. By the way, pin 1, what we're going to do is we're going to put these things with the pins up, not down. If you hook them down, you're going to be backwards. So the pins are up. I'm going to take this and I'm going to do what? Slide it in there. Oh, crap, bitch. That's okay. This is demonstration anyway. I'm going to slide it in there, right? You understand? I'm going to come up here and I'm going to push that jacket until it gets under that crimp, right? You understand that? I'm going to come up here and I'm going to look at the front. And what I'm looking for is I'm looking for these little old copper circles right here, which indicates I've got the thing all the way up to the watt, to the end. I'm going to come up here and verify my color code. Orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. I verified my color because once I crimp it, there's no undoing this. What will we have to do if we get the wrong color code? We have to cut it off, right? Then I'm going to take it and I'm going to insert it. So here's the guys that's going to actually do the crimping right here. This says this is for the 8, it says 8P, but that's 8 conductor. And I'm going to come up, and you can see where the tab goes, right there. I'm going to come up here and insert that, right? You understand? Then I'm going to do what? I'm going to come up here and crimp it. Huh? No, that was over there. And then I've got my connector on there. So what I've done is I've crimped it in the jacket. I double checked my code. I looked at the front and I saw what? 8 little old copper dots right there, which means I got it what? All the way in. And then we crimp it down, and this is a B. This is the 586, the 568B. Y'all see how we did it? And you can tell Rich has done a pretty good deal of them because I know my fingernails about the right length. I hadn't done one in a long time. Here you go, Dwayne. And that's network cables. You can buy pre-assembled network cables, but when you buy these network cables pre-assembled, they give you the length, right? You understand that? These, you can run this cable through walls. You can pull it anywhere you want to, and then you terminate it when you get there. The connectors themselves are not very expensive. We buy them in groups of 100. I don't forgot how much they are. They're not very. The crimp tools are not that expensive, depending on how much play you get out of them. I think you can buy the RJ11s. I think you can buy those at Lowe's. Huh? So look, I want y'all to look at the end and make sure you understand what I'm talking about, where you can see the little copper dots on the end. If you can't see that dot, it means that one of those cables is not all the way up to the end, and when you crimp it, it's not going to crimp good, right? Because that's what it's doing. It's actually taking the blades on that connector and pushing it into that insulation and cutting into that insulation and making your electrical connection. Blue, yeah. Green. So you round around, you roll the blues. The blues are not even used. The only two that's used are orange, white, orange, and the green, white, green. Those are two. So if you just went down there and put them in the right order, if you just said, I'm going to put orange, white, orange, I'm going to put these, well, you screwed up on Ethernet because now one of your signals is going to go down an untwisted pair, right? You understand that? So what we did there was we did a 586B. Now you could do a straight through cable. You could do all 568As if you wanted to, but that's just not the industry standard. The industry standard for a straight through cable is 2 Bs. And for a crossover cable, you do one of them what? A B, and you do the other one an A. And that makes a crossover cable. But you just can't make up the color code. You gotta break that twist. Right? You understand? That orange, white, orange, or that green, white, green, depending on whether you're doing an A or B. That blue, blue, white has got to go between that, and that's just the way they came up. So if you just make up your own color code, then you've lost the impedance of the cable because now your transmit might not be using the same pair, right? You understand? And you got to send them on the right pair. What they use is what is really made a difference. Used to send signals, we use something called single-ended. A single-ended transmission is basically obsolete. We don't ever use that anymore. Single-ended means what you do is you reference one wire to common. So what you do is you come over here and you send the wire out. And then one of them we would call the signal wire, and the other wire would be referenced to earth, ground, or common, which is what coax does. This is called single-ended. What we found out was to be able to basically eliminate electromagnetic interference, we use something called differential signaling now. So differential signaling means we don't use ground. We don't use ground. So what we do, I'm gonna put digital because it's a little easier to understand. So I'm gonna send a digital signal. Well, what we do is we have one conductor which uses this symbol right here. It's not, what we got to understand is this right here is a symbol. And what's a symbol? A symbol is what we use to represent things. So in differential signaling, the plus symbol means this is the uninverted signal. And what we do on the other wire, which they label minus, they send the exact signal, but they send it 180 degrees out of phase. If I can draw this good. So basically, it's a mirror image of that. And we came up with an amplifier called a differential amplifier. And these guys revolutionized communication. What a differential amplifier does, it amplifies the difference. So a common mode signal, which would be if I had an electromagnetic pulse come through this thing, it would generate that. That's what we call a common mode signal. A differential amplifier would reject common mode signals. The only thing it lets pass is what? Is differential signal. This, guys, has revolutionized communication. It's basically done away with coax cables. Now we use twisted pair cables, unshielded twisted pair cables, right? Because it uses differential signaling. USB is differential signaling. Ethernet is differential signaling. Serial ATA, which is the new hard drive interface, is differential signaling. We can send extremely fast data with basically very little desire for EMI. But if you don't send those things together, right? You understand. If you don't send the unshielded, the uninverted and inverted down a pair, then you screwed the whole cable up. So that's why you need to follow this color code. Even if it don't make sense to you, you need to follow this color code. By the way, you see some network cables that's only got 4 wires in them. They'll have orange, white, orange, green, white, green, but they still skip over those conductors that are not used. I've seen 4-wire network cables. I got one at home. The little clip broke off, and I was going to fix it, so I got me a connector, and I got over and I said, well, gosh, dog it. And I had to think, because I had to do what? I had to skip over those pins that wasn't used. I still had to use orange, white, orange, and green, white, green, but I had to skip over the blue, white, blue, right? And go over to the, instead of going to, I had to skip over to the what? 4th, 5th? I don't know how much. So those are the ones we're going to do. So what we're going to do is we're going to do punch downs. We're going to do butt splices. We're going to do a ring splice, which is basically the same. We're going to do, you're going to do a punch down. You're going to do a 66 punch down. But what you're going to do is you're not going to leave the cable. You're just going to pull out 2 wires out of a cable. You're going to use the punch down. We've only got one 66 punch down block over here. We got 2, but one of them's over another building. So what you'll do on that lab is you'll just put a tissue tape around it and leave it in here and put your name on it, right? Understand? We have enough for everybody to do a 66 punch down. And I'll tell you, the lab will tell you whether you're going to do an A or a B. But this guy here has actually got the color codes on for you, right? You understand? So this, y'all, I sent this around, right? We got enough of these for everybody to have their own their own 110 punch down. The A color code is what? Green, white, green. Blue, white, blue. Right? You understand? Orange, white, orange. I have to think about it. Orange, white, orange. So you have to reverse the orange. Everything's the same. Orange, white, orange. Green, white, right? Orange, white, orange. Green, white. It goes orange, white, orange. Green, white, blue. Blue, white, green. Brown, white, brown. So it would go green, white. It would go green, white, green. Orange, white, blue. Blue, white, green. Brown, white, brown. That makes sense? So all you're doing, Charles, is rolling the what? The orange and the greens. the orange, white, orange, and the green, white, green. So I know that I got the B down because we do a lot more straight through cables than we do crossover cables. So when I do a crossover cable, I got to kind of think about it. But all you got to do is just roll those two. Are we okay? Your lab will tell, but what's nice about this is you don't even have to know that because here it says for A. So on this punch down for A, I would use orange, white, orange. I would use brown, white, brown. And then over here for A, I would put blue, white, blue, green, white, green. So, and that's going to route it to the right plugs up here for you, right? You understand? That makes sense? So, and I think the lab tells you whether, and of course it's got the B's on here too. So what's nice about these little punch downs, you don't even have to think about the color code as long as I say, okay, I want you to do this punch down, either using the 568A or the 568B. It's when you come up here and put on these RJ45, these guys are not for you. Now the biggest problem we have, of course, is people will get confused on what pin 1. How do we identify pin 1?
Left or right?
Looking at it on the pin side, right? Not the, y'all understand what I'm saying? So what we do is we put it like this. And pin 1 is on the left. This is pin 1 right here. The problem we have is people will jam them in like this, and they'll do the right color code, but it's just exactly backwards. Then we'll have people, they'll crimp it, and they don't get their insulator where? Under the crimp for the insulator. And then when you do that, then the crimps out there on your wires are the only thing it's giving you not only your electrical, but it's doing your mechanical too, right? You understand? So what we need to make sure we do is get that jacket, and that jacket, it'll move. You probably see me. You can force that thing in there. And what you do when and it'll do it right. So if you cut it the right length, so your jacket ends up right there, then you're only out of that twist for about 1/4 of an inch, right? You understand? Right? You understand that? And so that's why when I strip it off probably 3 inches. That gives me the ability to do what? Get all the twists out of there. It also gives me the ability to have them nice long wires out there so I can arrange it into the right color, right? Y'all understand that? And once I get it into the right color, I clamp down on it with what? With my thumb, and I never take it off. I come up here and cut it, and then I take it instantly and stick it into the connector. And then once you get into the connector, guys, you got to do what? You got to let go because you got to push it in there. And you'll see that it's pretty flat, and it's real hard for if you got them in the right order for them to get out of the wrong order once you get it into the back of the connector. But then you got to do what? You got to double check that color code, right? Before you crimp it, you got to go double check that thing, because once you crimp it, then if you do it wrong, Rich is going to take off some points, and then what are you going to do? You're going to cut it off and redo it, right? So we had the guys last class actually made some cables that we're using on some of our computers over in another lab. We got over to another lab over there, and somebody had stuck all the cables. So we had computers that wasn't connected to the network. So are we okay? I think that's it for the PowerPoint too. No, a B and an A.
Oh, one end got to be.
Yeah, one end's got to be a B and the other one's got to be an A. If you run a straight through cable, you can do them both A's or you can do them both B's, but they got to be both. But the industry standard for a straight through cable, and why they did this, I don't know, is B. So you can go anywhere and buy a network cable, and if it's a straight through cable, you can look at the color code and it's going to be a B. Yeah, because that's what it does. It's transmit and receive are switched inside the switch so they match up. So that's not a DTE, that's a DCE. So it's designed for a straight through cable, right? You understand? These right here are designed for a straight through cable, right? So if I was to take a crossover cable and hook it over there, then I couldn't communicate on these networks. So you're right, the rolling of the transmit and the receive are done inside these DCEs, these data communication, these switches and these routers and all that kind of stuff. It's only when you hook two DTEs together, and you can understand you do that. You know, like when I need to program that PLC over there. Well, if I want to program that PLC, I want to take my computer and hook it up to the PLC, right? You understand? So I got to have a what? So a PLC considers itself to be a what? A DTE. A computer considers itself to be a DTE. So I have to use a straight through cable for a PLC. So that's why we got all these straight through cables. These crossover cables, so we can hook up our PLC. But that guy's got a switch on it. So if I was going to take, I could use a straight through cable from the PLC to the switch, and then the switch to my computer, because I'm going through a what? I'm going through a DCE, right? That makes sense. So if I went that route, I would have to use a straight through cable. If I went directly to the PLC, I would have to use a crossover cable. That makes sense. But you can literally connect two computers together. You can share files without being hooked up to a network. You can set up a little what they call a home group, work group, and you can share files, and you can just plug the two computers directly into each other. But you'll have to use the what? You'll have to use a crossover cable, right?
Let's say if you have one connection to your internet coming in, and you back to another computer, and you share that.
Some operating systems allow you to share an internet connection. You would have to look, like cell phones. You know, cell phones you can set up a lot of cell phones let you set up what we call a hotspot. So this right here can be set into a wireless access point.
So you can set the whole house up without being wired. Without using the wireless part.
If the computer, I don't know if Windows 7 supports a hotspot without going wireless. But if you've got a router, you can buy a switch. Good gracious, I just bought a switch, a 4-port switch for I think it was like $24, and that's what's in my office. So my office, my computer's on the network, my phone's on the network, it's wired, it's on the wired network, and then my printer's on the wired network. So I have to have a what? That little white switch you see on there, that's $24 at Best Buy. But they got like they got some big ones that you pay $100 for them. Like that guy right there, you know, you're talking about quite a bit of money for that. Cause look at all the ports on that. And not only does it have wired, it's also got fiber. Takes the fiber and converts the fiber over to what? Over to regular Ethernet. So that switch right there would cost quite a bit of money. And the access point is supposed to be up there. Now what this other thing hanging down there, I don't know. It looks like it might be a punch down there. I don't know. See the white blocks point? I believe that's fell down from somewhere. See what I'm talking about?
Yeah.
Huh? I wouldn't think so. Now, I think it's a punch down. I really do. I think it's a punch down. But it supports both fiber and okay, well, okay. Any questions? We got a little time for lab, guys. And this is in, so what we'll probably do, Thursday is we'll be in lab all night. Sounding like a winner. And then and then I think we have a test next Thursday, right? Is that right? Yes, we do. Yeah, on an 8-week term, guys, we can't shift test around. I'll tell you what, I can give you a 0 on it. So let's double check our calendar and see what we have. So we got a little less than an hour, then y'all can work on lab. And like I said, y'all come in Thursday and we'll be in lab all night, and then next week we'll start on copper. We're right on schedule, right? So first 4 weeks we're going to be on what? I'm sorry. First 4 weeks was copper. The next 4 weeks we're going to be on fiber.
So even though spring break is in there, you can't do it.
No, this is the fourth week. Test 2. This is the fourth week of the term, not counting spring break. If you count spring break, it would be the 5th week. Now, how do I know that? Because the 4th week occurs before test 3. So we just got them. So understand. So the actual second test, the second test is actually right after spring break, right after midterm. I think it is because I know my PLC class is next Thursday and they test at the same time. But since we've covered everything, I'll go ahead and look at the review, and I can go ahead and probably post a review. I thought I was the only one to do that. Y'all probably noticed that every once in a while. The previous test. It should be there. It's there? No, our test is Tuesday. Yeah, that's what so test 2 is right here. And then honors and awards on the 12th. It's during the day if any else getting awards. That's the only thing when Nancy, when we gave some awards out one year, the people didn't show up. So Nancy, every time we nominate for somebody, yeah, she said if you ask them if they say they're not going to be there, then we're supposed to nominate somebody different. She got embarrassed one time. We didn't have any of our people. They called the names out and they were there. So that's the one thing she wants us to ask. Huh? Well, yeah, but now the test is here. Honors and award is here, so you should be okay. This is the last day to drop the class, by the way. So I think everybody here is doing okay. And here's the final exam right here. So 1, 2, 3, 4. So 1, 2, 3, 4. So so this is midterm week right here. We got four more weeks after this. Well, I'm sorry. 1, 2, 3, 4. We have our final right here, right? So here, I usually don't like to start in the new material on the day of the test, but we're going to have a whole day of lab. So do y'all want to shift it around and have the test first, and then instead of lecturing and then having the test, have the test first? Okay. So we'll have the class test at the start of class, and then we'll start in fiber optics, which we've already got a little taste of it, but not very much. Okay, guys, y'all see what y'all can do. Got 45 minutes now. And my Charles didn't show up for his other class. Not you, Charles. Charles Kigler. You know, you've had classes with Charles, haven't you? Kigler.
I never had a class.
And yeah. Well, so he's taking another class, but it's an all lab class. It's called robotic projects. So it's a lab. So instead of teaching it, we come up and say, I want you to do this, I want you to do that, and they got to figure out how to do it on their own. CarCam was terminated like in February, I think.
I was going to the Humber race, and I got a hot ticket. I bought the
Yeah, they lost their grant. It was funded by National Science Foundation, and that hurt us too, because we got a lot of money from CarCam.
What, did they pick them up at school or what?
No, they quit. They didn't get funded. CarCam is no longer. It's been disbanded. There is no longer a CarCam. And the lady that was running it, she was really good at her job. She retired. And we did. There was a lot of